We have an example problem here. We have two loudspeakers, A and B in the figure, are driven by the same amplifier and emit sinusoidal waves in phase. Speaker B is 2 meters to the right of speaker A. Consider point Q along the extension of the line connecting the speakers, 1 meter to the right of speaker B. Both speakers emit sound waves that travel directly from the speaker to point Q. What is the lowest frequency for which constructive interference occurs at point Q? And then question B, what is the lowest frequency for which destructive interference occurs at point Q? Okay, so point Q is over here. Since the loudspeakers are driven by the same amplifier and the waves are in phase, same amplifier means they have the same wavelength, amplitude, frequency. Emitting the same waves in phase gives us our delta phi naught of 0. So constructive interference will be described by our equation, delta x equals m lambda. Destructive interference will be described by our equation, delta x is equal to this quantity of m plus 1/2 times lambda. Okay, in both equations, m can be 0, 1, 2, 3, so forth. It's asking us about frequency, so speed being wavelength times frequency, we can substitute in for wavelength speed over frequency. So our constructive equation becomes delta x is mv over f. So if we solve for f, we're going to have mv over delta x. To get the lowest frequency, we're going to need to use the lowest possible value for m, but that's not going to be 0. And the reason why is point Q over here is most definitely not the same distance from speaker A and speaker B. With constructive interference, if m is 0, then delta x is 0. That means the observer is the same distance from both speakers, which of course is not the case here. For point Q, we know the sound from speaker A, so x sub A is 3 meters. It has to travel 3 meters to get to point Q. X sub B is 1 meter. So delta x is the difference between these two. It's 2 meters. So coming back to our equation for constructive interference, if we cannot use m equals 0 because we have a delta x, then the next smallest value of m will be 1. That's what I will want to put in. Since we're dealing with sound and they haven't given us a temperature or another value of speed to work with, we're just going to use the 343. So if I go ahead and plug in our values, I get 171.5, but let's see, we have 3 sig figs. So 2.00, 1.00. So 172 hertz is the lowest frequency for which constructive interference occurs. And we specifically mean perfect constructive interference, where the amplitude is going to be twice what it was for either one individually. For B, lowest frequency for which destructive interference, let's go ahead and substitute in, again, the speed over frequency. So frequency will be this quantity of m plus 1/2 times the speed divided by delta x. This time we can use m equals 0. That is the smallest possible value for m. That does not refer to them traveling the same distance when we're talking destructive. So let's see, 1/2 our v, 343 meters per second, divided by our difference in distance. This lowest frequency, 85.75, but again, 3 sig figs, 85.8 hertz would be the lowest frequency for which we would get this perfect destructive interference.